Hi everyone, and welcome to this lesson on the development of Euler's method. With Euler's method, we are trying to develop a numerical method for approximating a particular solution to a given differential equation. If you think back to what we have seen so far, we have seen an analytic and algebraic method for solving a differential equation by using integration. We have seen graphic methods for solving a differential equation by the use of slope fields. And now we look at a numerical method for solving a differential equation when given an initial condition. And this is what we know today as Euler's method. It is named for Leonhard Euler, the Swiss mathematician who lived from 1707 to 1783. He first put forth this method in his own calculus textbook, which was published somewhere between the years 1768 and 1770. So it's been around a while. Let's try to relate this new method back to something that you've seen before, linear approximation. Remember, with linear approximation, you're trying to use calculus and derivatives to approximate a function value on a curve. And we talked about how really all you're doing is using the equation of a tangent line. So suppose here we have a function's curve. This would be our curve f of x. And you can see that I have the tangent line drawn right about here. That's about at the x value, at least when I tried to do this graphically. That was about at the x value of 0.5. So maybe we were trying to approximate that value. And you might remember what we did was we had a delta x value. We've seen that delta x value before, our delta value, back as far as the formal definition of a limit. We saw it again in terms of the limit definitions of the derivative. So maybe in order to approximate this value here, we would use maybe something right here. And notice how that difference between the actual curve and that same x value on the tangent line is pretty darn close. And that was the whole idea behind linear approximation, was that the closer we were to our target, the better of an approximation we would get. So therefore, using a small delta value would yield better results. That's sort of what we're doing with Euler's method. The difference, though, is instead of having an original function f of x from which we would have found with linear approximation a derivative from that point, what you're going to have to start with Euler's method is a differential equation, dy dx, or y prime. What we're therefore trying to do with Euler's method is obtain a good approximation of a function value without actually knowing that function's equation. As we saw with linear approximation, we're going to want to use a small delta x value that is going to dictate the size of our steps from one point to the next. Sometimes you will see this referred to in Euler's method problems as the step size, instead of actually calling it delta x. And one thing you're going to notice is that Euler's method is an iterative process, meaning each point for the solution curves builds off of the previous point. I'm going to walk you through a very graphical perspective of this first, just to give you an understanding of where Euler's method comes from and the ideas behind it. So what we're looking at here is a slope field, and you'll notice that I have a solution curve drawn through it. So one thing you're always going to be given when you start an Euler's method problem is the differential equation dy dx. The other piece of information you'll be given is the starting point. We'll refer to it here as x sub 0, y sub 0. The idea behind Euler's method is that beginning with the starting point you're given, so suppose that's my starting point. I'm going to mark that as x sub 0, y sub 0. The idea behind Euler's method is that beginning at this point, x sub 0, y sub 0, you are going to draw a line segment in the direction determined by the slope field. So obviously we're going to have something positively oriented. Think of when you drew your own slope field and you had those little soap cuts. That's kind of what you're doing here. Now, the question is, how long do you make that little line that you're going to draw in the direction of the slope field? Well, the key is the delta x value that you'll also be given. Usually delta x, you'll see something pretty small. 0.1 gets used a lot. The length of this line you would draw would be until you get to the next x value as dictated by your delta x value. Your next x value always comes from taking the previous x value, in this case x sub 0, and adding your delta x onto it. So maybe when I draw my line, maybe I land right here, and I'm going to refer to that as x1 comma y1. So the horizontal distance between x sub 0 and x sub 1, that's going to be your delta x. And again, you want that pretty small in order for Euler's method to eventually give you a pretty good approximation for your particular solution. So that's how you know how long to draw your little line. That's going to go in the direction of the slope field. And then you just do it again. So now starting at this point, the x sub 1, y sub 1, I'm going to go again, and once again, I'm going to make my line as long as whatever my delta x dictates, and I still need to go in the direction of my slope field. So notice I'm still going in the positive direction, and I'm going to call this x sub 2, y sub 2. So you'll notice that your x value is always coming from the previous one by adding on to the previous x your delta x value. So now that I'm here, I'm going to go again, and I'm still going upward this way, and I'm going to stop whatever is dictated by my delta x. I'm going to call that x sub 3, y sub 3, and I'll keep going. Now you're probably wondering, how many times do you have to do this? You'll generally be told how many steps to do, so far I've done 4 steps. And maybe I'll do one more. Now I have to go, see, it looks like I have to swing this way a little bit. And once again, I'm going to stop at an x value dictated by adding on delta x to my previous x value. So now I've gone 5 steps. Take a look at what's happened. The black curve that you see here, that black curve is an actual solution curve based upon a given initial condition. Notice what we have here though. Notice how what we've done is very much following the curve of that possible solution curve. Just a little bit above it. It's not too far away from it. Had I used smaller delta x values, I would have hovered closer to this true solution curve. And that's really what we're doing with Euler's method, is we're using this step-by-step process to arrive at a particular solution to a differential equation when given an initial condition. So maybe we were trying to approximate this one right here. Notice I'm not that far off really what it should be. And that's really the idea behind Euler's method, is that we're not doing any calculus here. We're really just drawing lines to arrive at a particular solution for a differential equation. So we have the x's taken care of, how we get from one x to the next. The question then becomes, how do we generate what our y values are for those x values? Well, we are talking lines, and if you think of your algebra, what comes to mind are forms of a linear equation, standard form, slope-intercept form, point-slope form. And that's really what we're going to make use of, just algebra, to generate these y values. Let's consider point-slope form of a line. And let's think of this y and this x as being the new point, and the x1 and y1 as being the point from which we are working. M, well, that's the slope of our line. And remember, you're given dy dx, which is a derivative, which by definition is the slope of that line. So perhaps think of the new y. I'm just going to call that y new. And y1, that's the point from which I'm working, the old y value. Our slope we can get by using our differential equation we're given. X is the x that I'm going to, so my new x value. And x1 is what I'm thinking of as my old x value, the one from which I'm working. We knew to get from one x value to another, that's where the delta x comes in play. So it makes sense that if we subtract and find the difference between our new x and our old x, that's going to be delta x. So think about what we have here. We're trying to find this, but we know this, we know this, and we know this. It stands to reason, a little bit of algebra. And if we add the old y coordinate over to the right side of the equation, we find that the new y that we're trying to obtain will be equal to the old y value plus the product of the slope and the delta x value. And that is the formula that we know as Euler's method. Now what we have here is what I like to think of as a very usable formula. There is, of course, a more formal mathematical statement of Euler's formula. So let's take a look at that for a second. Euler's method states that an approximation of the solution of the differential equation y prime equals f of xy. Think about what this means. This is saying that we have a differential equation, y prime. I easily could have referred to that as dy dx. That's going to be a function of both x's and y's. And if you think about a lot of the differential equations you've seen, remember how the x's and y's were both present in that differential equation? That's all this is saying, is that your differential equation could have both x's and y's in it, with the initial condition that f of x sub 0 is equal to y sub 0. So that's the original point, the starting point you'll be given. And the approximation is going to be given by y sub n is equal to y sub n minus 1 plus the function of x sub n minus 1 and y sub n minus 1. Now remember what f was referring to. F is referring to the derivative. So that is your slope times delta x. So really what we have here is simply a more formal statement of this. That's it. It's just another way to express it. It's the exact same thing. Delta x is going to be given to you. It's going to be a small non-zero number that serves as an increment or step size along the x-axis as you move from one x value to the next. And n is the number of incremental approximations you want to take. Hopefully that gives you a little bit of the background behind what we're trying to achieve with Euler's method. Let's now work through an example of how you can use Euler's method to actually approximate a real solution curve. You'll want to have your graphing calculators handy if you want to walk through some of this along with me. In this example, we are asked to use Euler's method to sketch a possible solution curve for the differential equation dy dx equals x times y, starting at the point 0, 1, and using a delta x value of 0.1. So we are going to make use of that nice usable version of the Euler's method formula. And what we're going to do is set up a table of values to help us work through this. If you were to search online for lessons on Euler's method and worked examples, you are going to see many, many ways of doing an Euler's method problem. What I'm going to share with you is just one of those ways. We'll be setting up a table to mimic this formula and just really generating the values off of our graphing calculator. So the table is going to look like this. We start, of course, with an x value. And remember, we were given our initial condition was the point 0, 1. So I know my original x is 0 and my y is 1. Now, this is really going to become my old y. This is the y from which I am working. If you think of the formula, the next thing I need is my slope, my dy dx. This is really the slope at the old y value. And all I'm going to do is substitute into the derivative I was given. Now in this example, remember I was given that dy dx is equal to x times y. So if I substitute my x and my y into this differential equation, of course I get 0. That is my slope. The next piece of that formula is that I need to take that slope and multiply it by delta x. Now in this case, remember delta x was 0.1. So multiplying my slope, my dy dx times 0.1, of course I get 0. Now remember how the formula goes. My new y value is going to be equal to my old y value plus my slope times delta x, and that will equal my y value. So if I do 1 plus 0, I get 1, and that's my new y value. If you apply this to the example we walked through earlier with our slope field, what we just found in that answer of 1 is the value of y sub 1. So now we're going to go through the process again, and that will give us our y value for y sub 2. And we just keep going. That's what we mean by an iterative process. You just keep repeating the process over and over until you are told to stop or you arrive at what you wanted to achieve. Remember, our starting x value was 0. So if we add on our delta x, that means our next x value is 0.1. Now, the y value that goes with that is what we had found earlier on the previous line. So the y new always carries down and really becomes now the y from which you're working, our y old. And we just go through the process again. we need to substitute into our derivative x times y to attain dy dx. So if we do 0.1 times 1, of course we get 0.1. Now we need to do that slope of 0.1 times our delta x value of 0.1, and that gives us 0.01. Now you actually finish out the formula. Remember, we're taking our old y value plus dy dx times delta x. So we have 1 plus 0.01, and that, of course, gives us 1.01. And that becomes our next y value. So I thought we'd carry this out a few times so that I can show you a really nice graph of what's going on here. My next x value is going to be 0.2 because remember I'm just adding on delta x. I carry down the previous y value and just repeat the process. I need my slope next by doing x times y. So I'd have 0.2 times 1.01. That gives me 0.202. Now I need that slope times my 0.1 for my delta x, and I get 0.0202. One thing you're going to notice is that we tend to carry out a few more decimal places, so it's not uncommon to carry it out to maybe 4 or 5 places after the decimal, and we really just do that for accuracy's sake. Finishing out the formula, we have our old y value plus dy dx times delta x. So we have 1.01 plus 0.0202, and that gives me 1.0302. My next x value would be 0.3. Bring down my previous y. This might be a good opportunity for you to pause this and continue on your calculations. I'm going to go up to 0.6. So remember, my y value for 0.6 is going to be this last one you calculate from the x value of 0.5. So once you find that and carry it down, you can stop. So why don't you pause the video. When you come back, I will have all this filled out for you, and you can make sure your calculations are correct. Let's see how you did. What you see here is the completed table up to 6 iterations. What we're going to look at now on our graphing calculator is what the graph of this differential equation looks like. Where Euler's method really has benefit is that it allows us to find particular solutions for differential equations that we don't know how to solve yet. You, of course, have been exposed to only the ones you can solve by hand at this point, but there's a lot out there that you don't know how to solve yet, and that's really where Euler's method at this point in your calculus learning has benefit. So let's take a look at the differential equation and its slope field graph. If you care to follow along, you'll want to clear out what you have under y equals. Let me show you how I have my windows set up. You might find it helpful to set yours up the same way. Our x's, we're just going to go 0 to 1, and we're going to make use of our x scale as that delta x value that we had, 0.1. Our y minimum, if you set that as a 0.5 and go up to a maximum of 1.5, and just for consistency's sake, I chose a y scale of 0.1 as well for that. If you go under y equals, we're going to graph the differential equation and its slope field. So we have x, and remember we hunt and peck for our y value. Now don't hit graph. Remember, we need to back out of this to our quit screen, and we're going to run that slope field program that you have installed on your graphing calculator. So this is the slope field for the differential equation dy dx equals x times y. And if you take a look at it and imagine what a possible solution curve could look like going through this, starting over here on the left, it looks like it's pretty flat at first, and then it does swing upward. So I'm thinking some kind of exponential equation is maybe what this might look like in the end for our solution curve. I've already gone ahead and solved this. And what I got was e raised to the 0.5 x squared. So like we guessed just by looking at the slope field, it is indeed an exponential equation. So this is the solution curve, the particular solution for an initial condition of the point 0, 1 lying on the original curve. So this is a graph of the particular solution to the differential equation dy dx equals x times y, given the initial condition of the point 0, 1 lying on the curve. Remember what we just generated by Euler's method. Our points that should lie on this curve. So I'm going to make use of my stat plot, which some of you might have learned to do. So what I did was under my lists, I set up those points that we had found. Notice the points I'm using are these first two columns. All right, they are the actual points on the curve. So I'm going to plot on this graph the 0.01, 0.01, 0.2, 1.01, so on and so forth. So I have 7 nice points here to have plotted. So that's what I set up under my lists. You don't necessarily have to do this part. You can just look at what happened online if you'd like. So you'll notice here I have those 7 points. I need to go ahead and turn on my stat plot really quick. There we go. And I'm going to graph it. Now, here's my blue curve. That is the known solution curve because I actually solved that by hand. You'll see here the 7 points that I just referenced on our earlier page. Notice how for values really close to 0, 1, which is what this first point is, notice how that curve is just perfectly going through those points. The farther I get from that initial point, notice how the points aren't so much on the curve. And that's the idea behind Euler's method. As long as you stay pretty close to your target, all right, in your initial condition, your values, your approximations are going to be pretty good. The farther you stray from it, they're not as good. Hopefully this gives you a little bit of background and understanding of what Euler's method is all about. It's all about finding a good approximation of a function value at a point without actually knowing that function value. And the catch is that we really want to stay close to that starting value. And the way we do that is through our delta x.